Students, in this session, I am discussing about design of thermoplastic injection molding tool. Shown here is the blackboard tester. The blackboard tester has got two parts. The body is made up of a thermoplastic material like ABS, and the erasing portion is made up of felt. Both are attached together using adhesive. We are going to discuss about how to manufacture this body of the duster using thermoplastic injection molding tool. We are going to design a thermoplastic injection molding tool for making this duster. The raw material for making this duster is in the form of granules. Now this is the raw material, which is in the form of a granule. This is available in the market. This has to be purchased and fed into the hopper of the injection molding machine. So now this is the injection molding machine. It has got injection unit, fixed platen, moving platen, and ejector cylinder. The fixed platen will not move, it is fixed to the base. Moving platen can be moved linearly for the purpose of opening and closing the mold. This is the component diagram. We want to make this duster out of ABS material, which is having a shrinkage of 0.7% for this example. The duster is having a wall thickness of 1.8. Let us see how to design a molding tool for making this duster. The designed molding tool has to be fitted onto the moving and fixed platen. After fitting the molding tool between the moving and fixed platen, then we have to move the injection unit close to the fixed platen. The raw material which is fed into the hopper will be melted in the barrel, and the granules becomes liquid. The liquid polymer has to be injected during the molding cycle. The designed molding tool is shown here. Now this is the molding tool which has been designed for making the blackboard duster body. This is the cavity. This is the injection core. The core is fitted onto a core plate. Two parallel blocks are there. Between the two parallel blocks, we have got the ejector plate, ejector retaining plate, ejector pin, and two return pin. And there is a base plate. As I told you, it has got two offs. So from here, this is core off. This is cavity off. The core off contains core plate, parallel block, base, along with the ejector elements. The cavity off contains cavity plate, screw bush, register ring. The isometric view of the exploded view of the core off is shown here. Core, which is to be fitted onto the core plate from the back side, and parallel block. One parallel block is shown here, other parallel block is not included in this view. And between the two parallel blocks, we have got 6 ejector pin, 2 return pin, ejector retaining plate, ejector plate. Then this is the base plate. In the assembly condition, this is how it looks like. The core off will look like this. So all this plate, core plate, parallel block, base. All these plates are joined together using a fastener running from the back side of the base. The HZR plate will be free to move along with the pins and HZR retainer plate. So this design uses 6 number of HZR pin for the purpose of ejecting the component out of the core. So these 6 pin are, so these are the 6 HZR pin. These 6 pin are fitted from the back side of this plate, HZR retaining plate. In addition, 2 retaining pin are also fitted from the back side of the HZR retaining plate. Once all the 8 pins are fitted, then it is closed with another plate called HZR plate. Both are fastened together. So this is the assembled view of the HZR mechanism used in this design. So these 2 plates are fastened together, and as a result all the element will be moving inside outside for the purpose of ejecting the component out of the core during the ejection cycle. The exploded view of the cavity of is shown here. This is the cavity plate with stirring sprue bush. So the cavity portion forms the outside shape of the cavity portion forms decides the outside portion of the tester, while the core decides the inside shape of the tester. After designing everything, after manufacturing all the elements, both will be closed. Core of and cavity of will be closed together. A gap is formed around the core. In this space only, we have to inject the molten material through a sprue bush. So the molten material, the molten polymer will be injected from the nozzle of the injection unit into the space through the sprue. So from the nozzle, the molten polymer flows through this sprue and it fills the space around the core. That is what shown in this figure. See here, the polymer from the injection nozzle flows through the sprue and it fills the gap around the core. So the injection cycle is over. Now we have to allow for solidification of the molten polymer. You have to pass water around the core and cavity for the purpose of removing the heat. In this process, the molten polymer solidifies during the cooling cycle, and once it solidifies, the component has to be ejected out. For the purpose of ejecting the component, we have to operate the HZR mechanism. If you look at the injection molding machine, there is one HZR cylinder. It will move HZR rod. The rod will be pushing the HZR mechanism of the tool that has been designed through a hole on this moving platen. There is a hole on the moving platen. The HZR rod of the machine will be operated, and it will push the plate. It will push the HZR plate towards the right side. So when the HZR plates are moved towards the right side, the HZR retainer plate and all the 6 pin, 2 retainer pin, all these elements will be pushed towards the right side. And the component which has been molded will be firmly sticking over the core side. So after solidification, the component will be firmly sticking over to the core side. So for ejecting the component, we are operating the HZR mechanism. So while you operate the HZR mechanism, the HZR rod will be pushing the plates, and this is the final position, and the pin, 6 HZR pin, 2 return pin will be pushed forward. So in this process, the component which is firmly sticking over to the core will be ejected out, and we are able to remove the component, and we are able to keep the mold ready for next cycle. So the component that has been ejected out of the core looks like this. So the component is formed along with this sprue portion. This sprue portion has to be removed by machining after fully solidifying the component. So the first component has been molded this way. So after ejecting the component out of the core off, we have to prepare the molding tool for the second cycle. So you have to bring back all the 6 ZR pin to the initial position. So for that, we are using 2 return pin. For the second cycle, we have to close the molding tool by bringing the moving platen towards right side. So when we bring the moving platen towards right side, the core off will be moving towards the cavity off, which is fixed. In this process, the 2 return pin will be hitting on the surface on the cavity plate. As a result, the 2 return pin will be pushed backside. When both of our core and cavity offs are closing, the return pin will be pushed back because of the closing action. As a result, the 2 return pin will be pushing the SR plate, SR retainer plate along the 6 pins. See here. So when the 2 return pins are pushed back during the closing action, the two return pin will be pushing the SR plate and SR retainer plate all the 6 pin, because both are fastened together. So the purpose of return pin is to bring back the SR mechanism to its initial position. Once the SR plates are brought back to its initial position, this is the final condition. So all the 6 pins have been retracted and the pins are in line with the surface of the core. Now the core and cavity are ready for injecting, for producing the second cycle. So when both the off are closed, all the 6 pins are retracted because of the force acting on the 2 return pin. Now the space is ready for injecting the second cycle, injecting the molten polymer for the second cycle. So let us decide how to arrive at the core and cavity dimensions. So from the part drawing, we understand that the shrinkage allowance of 0.7 has to be considered for deciding the core and cavity dimensions. The inner portion of the duster body is decided by the core of the molding tool that has been designed. The outer portion of the blackboard duster body is decided by the cavity portion of the injection molding tool. So now this is the part drawing of the core. So we have got 6 number of holes for operating the HTR pin during the extrusion cycle. As per the drawing, this dimension is 128. This is 130. So we have to account for 0.7% of shrinkage allowance. So accounting for 0.7% of shrinkage allowance, this dimension comes to 128.9. So 128 plus 0.7% of 128. So putting together, this is 128.9. So this dimension is 128.9 after accounting for shrinkage of 0.7% for this example. This is 130. So this is 130 on the component. This is the component dimension. So core dimension has to be arrived after accounting for a shrinkage allowance. So 130 plus 0.7 percentage of 130, this is 130.91. Similarly, all the other dimensions are arrived by accounting for a shrinkage allowance of 0.7 percentage for this example. Let us come to the part drawing of cavity. Now this is the cavity dimensions. So the cavity dimensions are arrived again by accounting for a shrinkage allowance of 0.7 percentage. From the component, all the dimensions refers to the inner dimension only, inner dimension of the blackboard duster. If this is 130 means, what is the outer dimension? 130 plus 2 times wall thickness. So 130 plus 3.6, 133.6. So we are to, so this dimension should be 133.6 plus a shrinkage allowance. So when you account for shrinkage allowance, it comes to 134.54. So this 40 is the inner dimension on the component. What is the outer dimension? 40 plus 3.6. So 43.6. So 43.6 plus 0.7 percentage shrinkage, it comes to 43.91. So that is shown here, 43.91. So like that, we have to account for shrinkage allowance of 0.7 percentage for this example. So this is the part drawing of the core of or core plate. So finally, so this is the cross-sectional view of the designed molding tool, which we have designed for producing blackboard duster body. In this example, the molten polymer from this sprue is directly reaching to the cavity. But when you want to make multi-cavity mold, the molten polymer will not directly reach to the cavity from this sprue. So when you want to design a multi-cavity mold, suppose you want to produce 4 number of duster in a single cycle, then we have to have 4 cavity in the molding tool. How the molten polymer will reach to the cavity? So from this sprue, it is reaching to the main runner. From the main runner, it is reaching to the branch runners. From the branch runner, through the gate, it is reaching to the cavity. So normally, a mold feeding system consists of sprue, main runner, branch runner, gate.